Howdy, welcome to Math 153, Elementary Statistics. I am Lance Curtis, and this is the lecture for sections 8.4 and 8.5. As you can see, 8.4 and 8.5 are the final sections that we're going to look at in Chapter 8. So let's dive in with the first of these two sections, 8.4, testing a claim about a mean. Here in this section, we're going to present methods for testing a claim about a population mean. Now, as with the confidence intervals that we made about a population mean, we're going to have the same key question, which is, do you know what the population standard deviation sigma is? If the answer to that question is yes, then we're going to use the normal distribution and calculate a z-score for our test statistic. If the answer is no, then we're going to use the student t-distribution and calculate a t-score for our test statistic. In reality, when you're working with this stuff in the real world, it's very rare that you know what the population standard deviation is. Very rare. We'll touch on that a little bit more later in the lecture. First, let's examine the instance when we don't know what sigma is. This is much more common in the real world. And when we have this situation, we have two requirements that we need to meet. These are basically assumptions upon which our methodology is based. So we have to meet these requirements in order for these assumptions to hold true. The first is that the sample is a simple random sample. The second is that the population is either normally distributed or that n is greater than 30. If the population is not normally distributed, but we have a sample size greater than 30, then the central limit theorem says that we can use a normal distribution to approximate. That's why we have the or n is greater than 30 as part of the requirement for normal distribution. Of course, if we're already normally distributed, it doesn't matter what the sample size is. Our test statistic is going to be a t-score, which we calculate by using this formula that you see here at the center of your screen. Pretty straightforward. Plug in what you know, punch out the answer. There's your t-score test statistic. Now, as before, when we were conducting hypothesis testing on population proportions, we're going to use either a p-value or the critical value to decide the test. So let's look at an example. Radiation emissions from cell phones. Here in the table at the bottom of the screen, there's a sample of radiation emissions that were measured in watts per kilogram for 11 cell phones. So we're asked to use a 5% level of significance to test the claim that cell phones have a mean radiation level less than 1 watt per kilogram. Now, if we look at the data that's there in our table and calculate some summary statistics, we find that the mean is 0.938 and the standard deviation is 0.423. So with these summary statistics, we now have what we need to proceed with our hypothesis test. But first, we need to check to make sure our requirements are met. So we weren't actually told anything about the sampling, so we don't know that we have a simple random sample, but we also don't have any evidence to suggest that the sample is not a simple random sample. So it's probably okay to assume, given the types of examples that we've seen so far, that the sample is a simple random sample. The next requirement is about normality, and our sample size 11 is less than 30, so we can't use central limit theorem to assume a normally distributed data set. That means we have to take our sample data and make a QQ plot to check for normality. When we do that, we get something that looks like this, and as you can see, there's nothing really super crazy about it. The points are generally along the line. There's no set pattern that we see one way or the other. So there's nothing really calling out that says this is definitely not normally distributed. So we're going to say the data appear to be normally distributed. So with that, the necessary requirements appear to be satisfied. So now we can proceed with our hypothesis test. We can express the claim that cell phones have a mean radiation level less than 1 watt per kilogram with what you see here on the screen. Mu is less than 1.00 watt per kilogram. Next, we write out our hypotheses. So the null hypothesis is going to be mu equals 1, and the alternative hypothesis is going to be mu is less than 1. Because our alternative hypothesis is using the less than sign, we have a left-tailed test. Remember, the inequality sign is like an arrowhead pointing toward the direction of the tail that we're using in our hypothesis test. So this is a left-tailed test because this is pointing to the left. Therefore, we have a left-tailed test for our hypothesis test. As was declared in the problem statement, we have a 5% significance level, alpha. And we're making a claim about a population mean. So the most relevant statistic is going to be the sample mean, which is x bar. We're now ready to calculate our test statistic. We use the formula that we saw previously. We plug in the values that we know. So our sample mean, 0.938. Our population mean is claimed to be 1, sample standard deviation of 0.423, and sample size of 11. Punch that out on your calculator and you will get negative 0.486. We're now ready to determine what our test results are. As we've seen previously, there's two ways we can go about it. The first way is by comparing our p-value to the significance level alpha. So you're comparing two areas together. The p-value is the area under the curve to the left of the test statistic. So if I put the test statistic here into my t-calculator, I find that the area, which is my p-value, 0.3187. So because that area, 0.3187, is greater than the area represented by the significance level, alpha, 5%, I'm going to fail to reject H0 because I'm outside the critical region. Now we can also compare the test statistic with the critical value. So if I find what my critical value is by putting in the significance level for my area, then that critical region is going to be bounded by the critical value, which we find is negative 1.812. I can also get the same critical value if I use a table. Now, because our test statistic is within the region, the critical region here, bounded by the critical value, then that means, we're outside the critical region. We're going to fail to reject H0. So the boundary of the critical region is negative 1.812. But our test statistic is over here by 0. It's negative 0.486. So it's outside the critical region, therefore we're going to fail to reject the null hypothesis. So either way, we reach the same conclusion. Because we failed to reject the null hypothesis, we conclude there is not sufficient evidence to support the claim that cell phones have a mean radiation level less than 1 watt per kilogram. Now, during the instances when we do know what sigma is, the population standard deviation, then we're going to use a test that involves a standard normal distribution. But as was stated before, it's very rare to find this in the real world. I mean, think about it. In what instance would you know what the population standard deviation is, but not know what the population mean is? So why would you run a test on a population mean that you don't know if you do know what the population standard deviation is? In reality, that's a very rare instance that you're going to find actually happening. But in the event that it does, okay, the procedure is essentially the same. We just have to calculate a test statistic z-score instead of a t-score. And the equation that we use is here on the screen towards the bottom left. Notice that this looks suspiciously familiar. That's because this is the exact same formula that we used to calculate the t-score with one important difference. Okay, here we're actually using the population standard deviation because we know what it is. Previously, when we were calculating the t-score, we were doing that because we didn't know what the population standard deviation was, and so we were using the sample standard deviation to estimate it. Here there's no need to estimate. We know what it is, And so we're going to use it to calculate our test statistic. Let's go back to our previous example, but add in the added information that the population standard deviation is 0.48 watts per kilogram. Now this is not going to change our null and alternative hypothesis. They're going to stay the same. But the values that we use to make the decision on our test results, those values will change. And here's how they change. First, we have a new test statistic. So using the equation that we just looked at, plug in what we know, punch that out on our calculator, and out comes negative 0.428. Slightly different value from what we had before. Because we have a new test statistic, that means we have a new p-value. Remember, the p-value is the area of the tail bounded by the test statistic. So when you change that test statistic, you're going to change the area that's bounded underneath the curve, which is the p-value. So now we have a new p-value of 0.3343. Notice we're also using the normal distribution instead of the t-distribution to calculate that area. And because we're using the normal distribution instead of the t-distribution, we're also going to have a new critical value, which we know from previous examples and work that we've done in previous sections is going to be negative 1.645. If you don't believe that, well then go ahead and look it up in the table or use a normal calculator there in your software, but it's going to come out negative 1.645. We still reach the same conclusion as before, however, okay, because our p-value of 0.3343 is greater than our significance level, 5%, we're going to fail to reject H0. We can't fit that area of the p-value into the area of the critical region. Therefore, we're going to fail to reject H0. We're outside the critical region. Likewise, if we compare our test statistic, negative 0.428, with our critical value of negative 1.645, we're going to find that again we are outside the critical region. So therefore we fail to reject H0 and reach the same conclusion as before, that there is not sufficient evidence to support the claim. That takes us to the end of section 8.4. So let's dive into this last section, 8.5, testing a claim about a standard deviation or variance. Key concepts in this section are that we're going to introduce methods for testing a claim made about a population standard deviation or population variance. Now, the methods in this section are going to use the chi-square distribution, which you may remember we were using to make confidence intervals about standard deviation and variance from Chapter 7. The same requirements that we had for testing population means apply here, but there's going to be an exception to that rule, which is that the requirement for normally distributed data is much stricter because the chi-square distribution is skewed. We're going to get to that a little bit later in the lecture. We also have a different test statistic, a chi-squared value that we're going to calculate. So we take the degrees of freedom, multiply by the sample variance, divide by the population variance, and that gives us our test statistic. Remember that DF is abbreviation for degrees of freedom, and the degrees of freedom is 1 less than the sample size. Let's talk a little bit about the requirements for testing a claim about a standard deviation or variance. So we have two main requirements that we need to satisfy. The first is the same that we've always seen, that the sample must be a simple random sample. The second requirement is that the population has a normal distribution. Notice there is no or n is greater than 30 part of this requirement. It's strictly normal distribution. So we don't have the central limit theorem anymore that allows us to assume that we have a normal distribution with a larger sample size. The data must be normally distributed, period. Now, the reason for that is that the chi-square test is not really robust against a departure from normality. Again, because the distribution itself is skewed. So what this means is that the test isn't going to work very well for the populations that have a distribution that's really far from being normally distributed. And it's this aspect of the test that makes the requirement for having a normally distributed population much stricter. So when you're testing a population mean, you can get away, per central limit theorem, with having data that's not normally distributed if you have a sample size larger than 30. But with testing for standard deviation or variance, you must have normally distributed data, or you cannot apply the methods that we're going to be using for hypothesis testing. That's just the way that it is. Let's look at an example involving supermodel heights. So the table that you see here in the center of the screen lists the heights in inches for a simple random sample of 10 supermodels. So if you consider that the heights of supermodels are believed to vary a lot less than the heights of women in the general population, because there's a certain type that fits the supermodel profile, then we can actually test the claim with a 1% significance level, as we're being asked to here, that the heights of supermodels have a standard deviation less than 2.6 inches. Well, our summary statistics that we're going to be interested in from this data set are listed here on the screen. There's a sample standard deviation of 0.89 and a sample variance of 0.79, or we're rounded to 0.8. Before we get into a hypothesis test, we need to check that our requirements are met. So the problem statement directly says we have a simple random sample, so we can check that one off. Next, we need to check for normality, and we do that by taking the data and making a QQ plot with it. So when we do that, we get something that looks like this, and there's nothing that's really calling us out as being not normal with this, so generally we're around the line. There's nothing that's out of the way here, so yeah, it seems that we have our requirements met. We're now ready to proceed with our hypothesis test. First, we can express the claim that the standard deviation is less than 2.6 inches as sigma is less than 2.6 inches. Next, we write out our hypotheses. So our null hypothesis is going to be that sigma equals 2.6. But our alternative hypothesis is going to be sigma is less than 2.6. Notice we're reflecting the claim in the alternative hypothesis. Notice that once again, we have a left-tailed test. So the inequality less than, like an arrowhead pointing to the left, that means our critical region is going to be on the left side of our distribution. We have a left-tailed test. The problem statement declares directly that we're testing at a 1% significance level, so alpha is 0.01. We're testing a claim about a population standard deviation, so the most relevant statistic is going to be the sample standard deviation. We're ready to calculate our test statistic now. We do that with the formula we looked at earlier. So we plug in what we know. Degrees of freedom is 1 less than the sample size. Sample size is 10, so degrees of freedom will be 10 minus 1, which is 9. And we plug in the sample standard deviation and the population standard deviation, which is actually coming from our claim, the null hypothesis, sigma equals 2.6. So we're just going to plug that in here. Punch that out in the calculator, and out comes 0.852. We're now ready to decide our test results. First, let's see what happens when we compare the p-value with the significance level alpha. So if I put in the test statistic into a chi-square calculator, or I could actually use a table to get the area, I'm going to get the same number, 0.0003. So that's a really small number. But when we compare that number, it's much less than the significance level. Therefore, we're inside the critical region, and we can reject H0. Alternatively, we can use our test statistic compared with our critical value. So calculating the critical value, put in the area for the significance level, and then I get my critical value here, 2.088. Now, because my test statistic is less than the critical value, I'm inside the critical region. Therefore, I'm going to reject H0. Because either way we reject the null hypothesis, we can conclude there is sufficient evidence to support the claim that the standard deviation of the heights of supermodels is less than 2.6 inches. No surprise there. As we were mentioning before, supermodels fit a certain profile, so it's not a surprise that they don't have as much variation as women in the general population. That brings us to the end of this lecture. If you have any questions, you know how to find me. Otherwise, I will see you in class. Thanks for watching.